Hi. So last time I had stopped towards the end of the lecture. I had mentioned 3 conditions one has to check to ensure that some set is a manifold. So let's see how one actually does that with some simple examples. Later on in the course we will have more non-trivial examples. To begin with, let's take M is an open subset of Rn. So the set I start with is an open subset of Rn. I would like to claim that this is an N manifold. So this, since it's M is an open subset of Rn, actually just a subset will do. We can regard M as a metric space, namely the Euclidean metric can be, gives rise to a distance function here. And since Rn is separable and M is open, M is separable as well. M is separable. So this takes care of the first condition. Second one is that locally Euclidean of dimension n. The obvious thing to do is we want to, so let P belong to M. I would like to find want an open set U which contains P and a homeomorphism phi from U to some V in Rn, where V is again open. So in other words, I want a chart containing P, i.e. a chart. This pair we have already called a chart U phi containing P. So given any point I should be able to construct this. But in our case M itself is an open subset. So just take whatever P is, take U to be M itself and phi equals identity, and of course V is also equal to this V here is also just take to be U itself. So this is completely trivial. So the locally Euclidean property is satisfied with just one chart in this case, and since there is just one chart, the question of transition functions being smooth becomes quite trivial. So the only time when the transition functions arise when you have U alpha intersection U beta is not empty. Since there is only one chart, the only transition function is the identity function. Because well, phi alpha equals phi beta, U alpha equals U beta, phi alpha equals phi beta. So when I take phi beta composed with phi alpha inverse, I just get the identity. Of course, the identity function this will be from M to M itself, identity, and one is done. So now for something more interesting, let's start with M equals S1. So for this, let's recall that Sn, the standard notation Sn, S superscript n, is by definition the set of all points in Rn such that norm x equals 1. This is the unit sphere with center, the origin in Rn. Here I have taken n equals 1. Oh, sorry, this is not Rn, this is Rn plus 1. Sn is the unit sphere in Rn plus 1. So S1 is the unit sphere in R2, which is just the circle, the unit circle in R2. So we would like to claim that S1, or more generally Sn, is a smooth manifold of dimension n. So let's begin by constructing some obvious looking charts on S1. But as I said, even before we construct charts, we have to verify that this is actually second countable and so on, Hausdorff. Again, since it's given as a subset of R2, we have a natural metric. Again, we have a metric on S1. And so the point is that once we have a metric, we don't have to worry about Hausdorff. And the only thing we have to do is check separability. Separability also is something one can see directly. It's just a matter of constructing a countable dense subset of S1. And this can be seen, for instance, by starting with the rational numbers in R and mapping R to S1 by cos theta, sin theta. That is just one way of doing it, but there are other ways also. So I won't go stress on this too much. So I'll just remark that S1 is separable as a metric space. What I want to focus on is I would like to construct charts on S1. The locally Euclidean of dimension 1. So how do we construct charts? So after all, what is a chart? A chart is something, it's given a point, we would like to find an open subset of the space around that point, containing that point, which can be mapped bijectively to an open subset of Rn. In this case, for instance, we want to map it to an interval in R. Now, it's if I start with any point, let's say some point here, then it's quite clear that as long as I don't include the whole circle, any arc containing this given point, any arc which contains this point, so the arc can be as big as one wants. So for instance, I can have an arc of the circle which goes all the way till here. Intuitively, it's clear that this arc can be mapped bijective in a homeomorphic manner to an open interval in R. So one can think of it like unwrapping, not unwrapping, rather straightening a piece of a string. So imagine a string has been put in the shape of a circle. So I just straighten out the string. That is a homeomorphism onto an open interval. In fact, there is this can be done, as I will show next, and but there is a, instead of taking a large arc like this, what happens if I take, I'll just take semicircles. So I'll divide the circle, entire circle, into 4 pieces. The first piece consists of the upper semicircle. I need open sets, so I cannot include the endpoints here. This is one open set which I'll call U1. Then I'll look at the lower semicircle. Well, I'll call it U1 plus. This one I'll call it U1 minus. Now, if I just take these two, the point is that they will not cover the whole circle. I need every point in the circle in M to be in one of these charts. So the problem with just these two is that, of course, this point and this point, which are actually just minus 1, 0, 1, 0, these 2 points are not in either U1 plus or U1 minus. So just to take care of these 2 points, I'll have to throw in 2 more arcs. So what I'll do is I'll take the left, oh, this may not be so visible, so let me take a darker color. So I'll take the left semicircle, the right semicircle. So this I'll call U2 minus, and this is U2 plus. So altogether I have decomposed S1 as a union of 4 arcs, U1 plus, union, U1 minus, union, U2 plus, union, U2 minus. And of course, from the very fact that S1 has been written as a union of these 4 sets, by definition means that every point of S1 is contained in one of these 4 arcs. Now, but we need a chart is not just an open set, we also need homeomorphisms. So let's start with U1 plus. Let's see what a homeomorphism can be. This is not quite a good picture. So this is u1 plus. So I would like to basically associate, so given any point here on this arc, I would like to associate a point in R. So what I'll do is, the obvious thing to do is, if I start with any point, I can just look at the x coordinate of that point. So to every point on this arc, there's a unique x coordinate, and that's going to be my map. So I define phi1 plus from u1 plus to, and the range of x values, so this is -1 and this is 1. So to -1 to 1, the map is defined to be phi1 plus of x comma y. Remember that since S1 is a subset of R2, every point of S1 has given by a pair of, has two coordinates x comma y, and I just define it to be x. Similarly, when I work with u2, rather no, this is not u2, this is still u1, but with a minus sign. When I have phi1 minus from u1 minus 2, I do the same thing, -1 to 1, phi1 minus xy equal to x. So this map phi1 plus is going to map the upper hemicircle to this open interval -1, 1, and this does the same from this to this. And it's as for the other two, well, so this was u2 minus, so I define phi2 minus from u2 minus again. So this time what I do is, if I do the same thing as I did by mapping to the x coordinate, I won't get a biject one-to-one map, because this point here and this point here, for instance, will get mapped to the same point. So anything above and directly below will get mapped to the same, will have the same x coordinate. But we just look at the y coordinates now. So anything here will get, I can map to this point. So, and the range of y values is -1, 1 again. So phi2 minus of xy is y, and similarly phi2 plus of x comma y is y. So even the right side, I just take a point, look at the y coordinate. That's going to be my homeomorphism. So, well, I've defined maps. It remains to that phi1 plus or minus, phi2 plus or minus, these four maps are homeomorphisms. Fortunately, we will not have to do this kind of very detailed calculations subsequently, but at least once we can go over all the details. Now, what does it, let's do it for phi1 plus. Phi1 plus is a map from u1 plus to -1, 1. Given by phi1 plus xy is x. It's quite, it's clear that phi1 plus is bijective. In fact, one can explicitly write down the inverse map. Phi1 plus the inverse acting on some real number t is just, so I am given the x coordinate, I would like to recover the unique point on the upper hemicycle corresponding to the x coordinate. So we know that that is the y coordinate has to be square root of 1 minus t squared. The positive square root of 1 minus t squared will give me the. So I have explicitly constructed an inverse. The moment you have an inverse, of course, the existence of an inverse is equivalent to this map being bijective. So we have the bijective part is taken care of, and also why are these two, and then one has to check that Phi1 plus and Phi1 plus inverse are continuous. So let me quickly say why that is the case. One easy way to see that is the map xy going to x. This is a map from R2 to R is obviously continuous. Therefore, its restriction to S1. The point here is that the topology on S1 can be regarded as coming from the metric induced by R2, or one can just look at the topology on R2 and take the subspace topology on this. It's the same thing. So therefore, if I have a map on the bigger space, its restriction to S1 is continuous. Now, as for the inverse map I wrote down already. It is t going to t square root of 1 minus t squared. Well, this I can just regard it as a map from minus 1 1 to R2. Now, when I have a map from say an interval into R2 and I want to check its continuous, it's the same thing as checking the continuity of each component function. The first component is t goes to t, the second one is t goes to square root of 1 minus t squared, t going to t, t going to square root of 1 minus t squared, both are continuous. Therefore, from here to here, Phi1 plus inverse is continuous. And if I regard, again because of subspace topology and so on, so therefore if I regard it as a map into S1, this is continuous as well. So this proves that what we have shown so far is that it's a topological n manifold. Therefore, S1 is a topological 1 manifold. Now now we have the task of the last step would be transition functions are C infinity. Now first of all, let's just quickly observe what possible transition functions can arise. This is one, So u1 plus, u1 minus, u2 minus, u2 plus. So I have 4 charts. Now transition functions are defined only when 2 charts have non-empty intersection. u1 plus and u1 minus do not intersect. Similarly, these two do not intersect. But u1 plus intersects with u2 minus, u1 plus also intersects with u2 plus, and similarly u1 minus intersects with u2 minus, u2 plus. So altogether, etc. So altogether we will get, so there are 4 possible intersections. So we will get 4 transition functions. Now let's quickly see what, I'll just check one of them. So let's take u1 plus intersection u2 plus. So u1 plus was here and then u2 plus was this. Their intersection actually is just going to be this, the open arc u1 plus intersection u2 plus. This is, however, the transition function is not defined on u1 plus intersection. It's rather the transition function here phi1 plus was mapping this to this portion, and the transition function was mapping to -1 to 1. So if I look at this, so both phi1 plus map u1 plus to -1 1, phi2 plus does the same thing. Of course, it's a different map. Now this intersection, so recall that the transition function was defined from phi1 plus of u1 plus intersection u2 plus to phi2 plus of the same thing. Now this phi1 plus of u plus intersection u2 plus, in other words of this portion, this is just, so phi1 is, the map phi1 plus was just looking at x coordinate. So x coordinates for this arc, it varies from 0 to 1. Similarly, this was looking at y coordinates. Y coordinates also varies from 0 to 1. So 0 to 1. And this was phi1 plus inverse composed with phi2 plus. So I have a map from 0 1 to 0 1. I have to see what it is. Well, I already have a formula for phi1 plus inverse. Phi1 plus inverse t was t square root of 1 minus t squared, and phi2 plus was just looking at the y coordinate. So therefore the transition function phi1 plus inverse composed with phi2 plus acting on, so transition function is from this open interval to this open, it will take input as t. So when I first do phi1 plus inverse, I get this, then I look at the y coordinate, therefore I get this. So I'll put this in. So this is the explicit formula for one of the 4 transition functions. All of them will resemble this. One of them, 2 of them will, another one will be exactly have the same formula. The other 2 will have negative signs in front of this. So this is what, and the point is that this map square root of 1 minus t squared is a infinitely differentiable function from 0 1 to 0 1. If I included 0, then this would no longer be infinitely differentiable, but I am in the open interval, so I am fine. So this is a C infinity function. Similarly, one can check that all the other 3 transition functions are C infinity. So that proves that therefore S1 is a smooth 1 manifold. Now this is extremely cumbersome if one had to do this proving that something is a manifold involved all these steps. It would be a very tedious task, but fortunately there's a powerful theorem which will give us large classes of manifolds without having to explicitly construct charts. But even for the case of S1, it is possible to cover, just use 2 charts and just check one transition function. So I will mention that it will work for all Sn. So in my next lecture I will return to the case of spheres and show you the construction of some nicer charts. So all right, thank you.